Section 2.3, day 1, part 1. Again, it's a rather beefy section, so we'll take it over 2 days in a normal lecture format. So I've broken up the lecture videos the same way. So this is day 1, part 1. The section title is Underdetermined and Overdetermined Systems, which is a pretty good title. What does it mean? Well, for us, it means the infinitely many solutions and the no solutions that we saw in section 2.1. So that's what we're going to look at, is how do we recognize when we have an infinite solution and a no solution when we're dealing with Gauss-Jordan. So this is actually case 2, and this matches up with the case numbers that we used clear back in section 2.1. So if you go back to your notes for section 2.1, you'll see what case 2 is referring to. This is what happens when the two lines are on top of each other or are essentially the same line. So this is our infinitely many solutions case. So let's deal with one of those. So what we're going to do is we're going to start off by solving this system, x plus 2y equal to 4, and 3x plus 6y equals 12. So we'll do the same Gauss-Jordan again. This is nice to give us practice at Gauss-Jordan. We're going to take this into our augmented matrix. I'll keep this as row 1 because I have my 1 where I need it already. So I have a 1, 2, 4, and then I have a 3, 6, 12. We've got our 1. Let's go get our 0 where the 3 is. So we're going to take row 1. Sorry, we're going to take row 2 minus 3 times row 1. So row 2 minus 3 times row 1. So 3 minus the 3, going to give us our 0. So 3 minus 3 is a 0. We're going to have 6 minus 6, which is 0. You're going to have 12 minus 12, which is 0. And as you can see right here, this equation down here with this row of all zeros is the same thing that occurred in section 2.1 when we were adding the equations together. Because 0 does equal 0, we consider this to be a true statement, which means this is an infinitely many solutions. If we were graphing them, these two lines would graph as the same line. That does tell me that I now need to go to parameters. So we're going to use parameters. And in this section, what they do is the author lets whatever the last letter is you're using be t. So in this case, because we have x's and y's, y is the last letter of the alphabet, we're going to come in and let y equal t, and then we're going to rewrite x in terms of t. So I'll pick off the top equation. That would have been x plus 2y is equal to 4, but we now know that y is a t. So x is going to be equal to 4 minus 2t. So our solution would be 4 minus 2t, comma t. So it's a dependent system. If you give me a value for t, which is our y, I can give you a value for x in terms of that value of t. So it's a dependent system. Let's go with a 3x3 equation just to show you how you use the parameters when it's a little bit larger system. So as an example, another example of case 2, what if you're given 1, 0, negative 1, 3, and then we have 0, 1, negative 1, 5, followed by 0, 0, 0, 0. So again, I see this row of zeros. So that makes me that tells us it's an infinite solution, which tells me to use a parameter. So these would be x, this would be y, this is z. So the last letter in the alphabet is z of the 3 that we're using. So we're going to come in and let z equal t. Okay, I don't have the original equations to work from, but I do have what this matrix tells me. So I'm going to go to that top row. So from the top row, we have x minus z is equal to 3. But wait, we're no longer using z, we have a t. So x would be equal to 3 plus t. So now I have a formula to give me my t, or my x in terms of t. Okay, and then the middle row, which is what? Y minus Z is equal to 5. Again, I'm going to replace the Z with the T. Now I have Y minus T equals 5, or Y equals 5 plus T. So now we have a solution. And again, in alphabetical order, X is first. That's the 3 plus the T. Y is second. That's 5 plus T. And then finally Z, which is just T. So now if you give me a value for T, I can tell you what the X and the Y are that are still on the same intersection of these planes. Infinitely many solutions. They all depend on what you pick for T. Okay, so what about the no solution case? So let's tackle one of those. So this was case 3 from the lecture in section 2.1. Case 3. And again, that's from the section 2.1 lecture is what I'm referring to. Our equation this time, our system is 2x minus 3y is equal to 5. I also have 4x minus 6y is equal to 2. So let's go do a row reduction on this one. Again, you can do it in any order you want. I don't have a 1 in either one of these spots, so it doesn't do me any good to swap rows. So I'm just going to write them straight over them here. So I have 2, negative 3, and 5 is my first row. In the matrix, we'll have 4, negative 6, and 2, and there's our augmented matrix. We know we need a 1 right here. We're going to come in and cut this row in half to get that. So we'll get what? 1, negative 3 halves, 5 halves. I know you're cringing because we're at fractions again. Copy the bottom row because we're not manipulating it. Now I need to come in and get a 0 where the 4 is. So to do that, we're going to take row 2 minus 4 times row 1. And by now I'm hoping you're a little bit more comfortable manipulating these matrices. So 1, negative 3 halves, 5 halves. Okay, so we have 4 minus 4, which is 0. We have negative 6 minus 4 times a negative 3 halves. So that'll go into that too. That's going to make that a positive 6 minus 6, which is 0, which we're kind of expecting. In the last spot, we have 2 minus 4 times 5 halves. That's 10. 2 minus 10 is a negative 8. And I can stop. There's no way I'm going to get a 1 right here without messing this up. I'm done as far as the matrix manipulation goes. We now see that the bottom row tells us that no x, 0x, 0y is equal to a negative 8. So because this is a false statement, 0 equals a negative 8, which is a false statement, we know that this is a no solution. So that row of 0 is equal to a constant tells me it's a no solution. Okay, and that's what happens whenever you have the number of equations is equal to the number of variables. So we've done 2 equations and 2 variables and 3 equations and 3 variables. Day 2 of the lecture deals with what happens when you either have more equations than variables or more variables than equations. That's what's coming up next.